Okay, welcome back. So today we're going to be looking at neural cellular automata, which is yet another model which is fairly recent. I think 2019, maybe 2020. I'm not sure. Around there, maybe a bit before. And it's one which has become pretty popular. We'll see exactly why. So the slide, as usual, is here. Some things. So I have the link here on the Notion, which I'll also put on the website. So you can go grab it either from the Notion. I think the Notion is already on the website. Let me check. It should be this one. Yeah, perfect. Okay. So you can either grab it from the Notion, or I will also put it on the website. And for the people who are officially registered to the course, I will also send by email. So this is just to vote for which day you are available for the presentation day. For now, I put as availability the last week of May and the first week of June. And if it's really not possible there, we'll try to move it. One other thing, next week there will probably be no lecture. And then there will be again lecture the week after this one. We'll confirm it to you. It depends a bit on Clément, how he's available. And I think that's pretty much it about the technical, the administrative stuff. So we can start right away. So are there any questions from previous course? Usually not, but never hurts to ask. Okay. So neural cellular automata. So what are they? So before going into explaining what is this model, let's motivate a bit. Let's trace a bit the path of how you could come up with such a model. So when you design alive systems, let me zoom in here a little bit. Yeah. So when you design alive systems, what you're looking for, at least often you're looking for emergence of complexity, right? So in most systems, we want to have some sort of emergence. And so emergence is not very well defined what it means. But the idea is that there are some things that happen without you explicitly coding them. So you code some simple rules, and it turns out that when you put a lot of particles, something unexpected happens. So yeah, so usually what you do is that you choose some basic rules guided by some broad principle like symmetry, for example, and you hope that as you make the system evolve, something emerges and you get interesting behavior. But of course, this is something very hard to do, right? By definition, almost, because you expect something very complicated to happen from some basic rules and a lot of degrees of freedom. So it's very hard to predict what a change in the rule will make in the overall behavior. And so usually you're a bit blind, okay? You try some stuff, usually common sense, we have some sort of intuition of what will work, but it's generally very hard to get something complex by definition, okay? So one nice thing would be that if we could somehow make a small change in the rule, look at the dynamics, look what this small change caused, and then get an idea if this small change was positive or negative, then go back, do a small change, and so on and so forth, so that you kind of inch towards something interesting. Okay, so this approach seems interesting. Of course, it has some problem. If your system is chaotic in your rules, I mean, a small change could completely change the dynamics. So you could not really have any feedback on what changes are good. But okay, what I described here of doing a small change, looking at what are the changes, and then going back and doing another change, small by small, little by little, sorry. This is more or less exactly what machine learning does, right? So the game plan for today for designing alive systems is as follows. So we choose a set of rules. So this is the space of rules that we will consider. And we choose a space of rules which has a decent amount of free parameters. Then we choose a transition function. Okay, this is essentially choosing a rule, but we restrict to transition functions which are differentiable in these free parameters. Okay, so we can take a derivative of our rule with respect to the parameters. And third, we choose a fitness function. So something that quantifies how successful is our current rule. Okay, for example, if you want a cellular automaton to have distinct solitons, a fitness function could be the number of solitons that appear after 10 seconds, or something like that. And so once you have these three elements, using the magic wand, which is machine learning, you can just train the parameters of your rule to optimize your fitness function. Okay. And in principle, you'll be able to get something which is interesting at the end. Okay, I don't know if you can profit from that. Probably you can, but let's see how it works. So here, just to put everybody on the same page, because not everybody necessarily has seen machine learning, I just want to make a very, very surface explanation of the main tool that people use in machine learning, which is gradient descent. Okay, it's extremely simple, and then showcase exactly how do we use it in machine learning in a very simple example. So in 10 minutes we'll be done, so that everybody's on the same page about the tools we will use today. So gradient descent. What is gradient descent? Well, essentially it's using the gradient to inform on the direction you should change your parameters to get a better score, right? So let's start by defining what are our moving pieces. So we have, first of all, a set of input values. Okay, we will take them to be a vector. Okay, it can be also a matrix, a tensor, whatever, but you can always arrange your set of input values into a vector, and we'll assume for simplicity that it is a vector of real values. Okay, so here r to the I, we have a I-dimensional input vector, which is what we get for free as an input. You could think of it as an initial condition, for example. Then you have a complicated function, which is called f theta, which takes your input values and it maps it to another vector, which is the output values. Okay, again, a vector of reals. So this f theta of x is our black box magic machine. Okay, it's a function that depends on a lot of parameters, theta, which we also say that they're neatly arranged in a vector of real values. It takes an input and spits out an output using these parameters in some way. Okay, don't worry for now about the specifics of f theta. And then the third element, okay, remember all these elements that we have here. So we defined something which is called in machine learning a loss function. This is just a function that takes the outputs of your model and some potentially additional auxiliary information, which we call S, and it returns for you a real number. And what is this real number? What does it represent? Well, it represents how well the output corresponds to our expectation. Okay. So the loss, in particular, the loss quantifies the quality of the output by telling you how bad it does. Okay. The higher the loss, the worse the output. So the objective that we have, if we want to get what we want, is to specify a loss. And then we'll be minimizing the loss, because the minimum of the loss is where the output is at its best, right? By definition of the loss function. Okay. So what we want is choose the parameters theta correctly, such that when we apply the loss function on the output of our network, we get a low number. Very good. And so we want to use the gradient descent algorithm to compute the parameters. And so as implied in the name, we will need to be able to compute gradients to apply gradient descent. And so what we'll do is we will assume that our loss and our black box f function are at least differentiable in the parameters theta, right? So we can take the partial derivatives of f with respect to the parameters, and same thing, partial derivative of L with respect to its inputs. So in practice, sometimes they may not be differentiable in a few select points. Turns out that things still work. But we'll assume they are differentiable just for simplicity. So then the gradient descent algorithm is very simple in what it does. We want to optimize theta to minimize L. So what we do is we just, okay, we cannot solve the equation. Okay, we could write an equation that we'd like to solve. Okay, the theta that minimize L, it's at an extremum of L, so the gradient of L should vanish. And so we can write a bunch of equations. But because the f theta of x is a very complicated function, we cannot solve this analytically. So we do it numerically. So what do we do? So we take an input x that is given to us. We run it through our function. We run it through our loss. We get a score. And then we compute the derivative or the gradient with respect to the parameters at this precise location. This you can do if f theta and L are functions that you can differentiate. Okay. If they are composed of polynomials, the known function, you can do that. And then what you're going to do is you're going to update your parameters such that they get a little bit closer to the direction that the gradient is telling us, right? Because the gradient here, what it tells us is the direction for the thetas, which has the steepest ascent in the loss, right? That's the definition of, that's one property of the gradient. So if we want to reduce lambda, all we have to do is take our thetas, update them to theta prime by subtracting the direction of the gradient. Okay, we just subtract the value of theta with the value of the gradient at the current point. And in principle, we should get a theta prime, where with this theta prime, if we run the neural network again, we'll get a slightly smaller loss since we followed the descent of the loss. Okay, so this is pictorially what's happening. It's extremely simple. We're just putting a ball and letting it roll on the hill of the loss. So this orange here is a plot of the loss function. Here they call it cost, as a function of our weights or our parameters. So if you start with parameters which is this one, you compute the gradient, which is this dashed line, and you update your weight to go a little bit towards the opposite of the gradient, right? And you do this over and over again, and you see that you roll towards a local minimum. Great. So yeah, and so here, just I didn't say, so this lambda here is what is called the learning rate. And this is a hyperparameter that is not learned by our algorithm. We just have to choose it. And this is just how much you want to update theta prime. Okay. And okay, you have to choose it not too small, otherwise your thing is too slow, but not too big, otherwise you will tend to bounce around the local minimum. And yeah, and that's pretty much it. That is on what machine learning is based. All of machine learning is based on, not all of it, but a big part of it. So when you see this, you might say, okay, there might be a few problems with this approach, right? So what if we have some local minima in our loss, right? What if our loss is something like this? We start here, we get lost, we get stuck in a minimum which is not optimal. What if, yeah, so the problem is that here when we do an update, we evaluate this gradient on a specific point x, right? But we want to minimize the loss on all possible inputs x. So since we are not doing that, why do we expect that the parameters that we find will generalize well to other inputs which have not been seen? Okay, nothing is telling us that in the algorithm. Then another problem is that it's very hard to come up with a loss, or it depends on the problems, but often it's very hard to come up with a loss which really encapsulates what we want to do with the neural network in a single number, right? We have to assign a single number, which is the score of how well it behaved. So how do we make sure that a small loss is well aligned with what we want the neural network to do? Yeah, that's another question. And then we have the question, okay, why would this work? This seems extremely simple. I mean, you have thousands of parameters, you're just rolling down the hill. It seems very far-fetched that it would work. So all these questions essentially have no answers yet. So these are some of the big questions in machine learning. We just know that empirically it works reasonably well, so we'll just assume that it's fine and we'll move on. So I want to finish here with this crash course just with some technicalities. So we said that f theta of x is just some complicated function of the parameters. But usually what we do is we organize it in what we call a neural network. Okay. Neural network is very simple. So it just means that our function f theta of x will be organized as a composition of simpler functions, which we call layers. Okay. So we have several layers here, which go from RH to RH plus 1. And one example is this. So if we have a two-layer neural network, what this means is that our function f theta is just layer 1 that depends on some parameters theta 1 applied to x. And then to the result of that, we apply a second layer. Okay, so that way we break up our function into layers, and we'll see that it makes things simpler. So in this particular case, with this notation, we start from an input that has dimension I, so this is the h1. Then through L1, the first layer, we go to a dimension h2 vector. And then through L2, we go to dimension h3, which should be the output dimensions. Okay, and so this is just a piece of nomenclature. The layer here, h2, is called a hidden layer simply because it's neither the input nor the output layer. So from an outside observer, he doesn't see this layer. That's why it's called hidden. Okay, it's in the middle of the neural network. And you can, of course, have several hidden layers if you want. So very often layers, what is a layer? It's still a free function that we have to choose. So very often they are very simple. It's just an affine operation followed by a nonlinearity. So an example is L theta of x might be mx plus b. So this is a matrix. So we multiply our vector and we add some bias, it's called, another vector. So here the parameters are the entries of the matrix and the entries of this vector here. And then on top of that, we apply some function sigma, which is a nonlinear function. And the way we apply this function sigma is we apply it individually to each element of the vector. And this function sigma is very important, although it carries no parameters. Okay, it's completely fixed. It's very important because otherwise you can chain as many layers as you want. It's just a composition of affine operations, which just gives you a big affine operation. Okay, so if you didn't have these sigmas in between the layers, essentially, you would just get a big linear function of the input, and you cannot do much about this. Okay, you can just learn lines of the input, which is not very powerful. Okay, so another small remark is that in the example we have given, we computed the loss on a single data point, x here, then do the gradients, etc. So in practice, what we do is that we average the loss over a bunch of data points, x, y. So we call them a batch of examples. And then we do the gradient descent step on this average loss. Okay, why do we do that? Is because we want to find parameters which are good essentially for all our data points, not just each data point individually. So if we take a bunch of data points, we'll be more aligned with this goal of finding parameters which work for any input. Okay, and finally, to compute this partial derivative here of the loss, we do it by what's called backpropagation. So this is a very fancy name, but this just means we apply the chain rule to the layers. Okay, so our function here is just a composition of several layers. How do you compute the derivative of a composition of function? Well, you apply the chain rule. Okay, so that's what people in machine learning call backpropagation. Why do they call it backpropagation? Well, it's very simple. So you have your network with the layer arranged one after another. And when you want to compute the gradient with respect to parameters in the first layer, it's just the ordinary derivative, right? You don't need the chain rule. Then if you want to compute the derivative one layer deep, you need to do the chain rule with the first layer. and so on and so forth. So each time to compute the derivative of the k layer, you need to do the chain rule with the layer which is one step further. And so the way you compute the gradients for all the layers is that you start at the deepest layer, compute it, then use the chain rule to compute the second layer, and so on and so forth. And so as you can see, you're doing propagating back from the end of the network to the beginning of the network, computing the derivatives with the chain rule. And so that's what we call back propagation. But it is just the chain rule, nothing more fancy than that. Well, the implementation, technical implementation, it's quite fancy, but in theoretical terms, it's just the chain rule. And so here I have the first question, which might be many people might be familiar with it, but the question is right. So is the rectified linear unit, which is this function here, is it, in your opinion, if you know, you know, but if you don't know, is it a good nonlinearity to apply to the neural network? So obviously it's a nonlinear function, right? Here it's linear, but here it's cut off to a constant line. So the full function is nonlinear. So do you think that it's a good nonlinearity to use in a neural network? You can just answer from your gut. I mean, if you know, of course, you know the answer. But okay, let's see what people think. So the code is here, by the way, if you want to join. Okay, I'll let you vote. We'll see the vote a bit later. Let's continue meanwhile. Okay, so this is gradient descent. And now we want to apply gradient descent to artificial life systems. So how do we do that? So first we have to identify the different components. So what are the parameters in an artificial life system? Well, this is obvious. This is just all the knobs that you can turn in your choice of rules, right? So when you choose rules, you have a set of parameters, and this will be the parameters of our machine learning algorithm. So there is only one thing to keep in mind, is that in machine learning, as we said, so we shown the thing that we'd explain works for parameters which are real numbers, okay, for two reasons. So if you have parameters which are more higher dimensional, let's say, than real numbers. So for example, my free parameter is a continuous function, like in reaction diffusion, okay? It will not work easily with machine learning because we have to compute this partial derivative with respect to parameters. So here you would need to compute a partial derivative with respect to a function. Okay, it becomes a functional derivative. Things become complicated. So we'll have trouble dealing with too general of a parameter. And at the other end of the spectrum, we'll also have trouble if we have too granular of a parameter. Okay, see, if we have parameters which are discrete, like, I don't know, in the game of life, the number of neighbors that makes you alive in the next step, you cannot do small adjustments with the gradient descent, and so it will not work. Okay. What will be the input? Well, this will be simply the initial state of the world of the automaton, very simple. The output, again, it will probably be the final state of the automaton after you evolve it a bunch of time. And what will be the function f theta that goes from input to output? I'll just be the application of the evolution rule of the cellular automaton. Okay. The only thing is that we might want to apply the evolution of the cellular automaton many times before looking at the output, right? Because we want to, for example, in Lenya, if I want to teach a creature to move, I need to do many evolution steps to see if it learned to move, right? I cannot just evaluate this after one evolution step. So here we introduce this notation here, f theta t of x. So this will denote the application of the transition function repeated many times such that we evolve the automaton for a time t. Okay, so this means evolve the automaton given input x for a time t. And then we must choose the loss, and this will be completely free, and it will be probably depend on the final state of the automata. So let's go a bit in the poll to see what people shown. Yeah. So most people said yes, which means I think either people saw that it was obviously a trick question or they already know about machine learning. So yeah, I just wanted to put these questions here because the first time I saw this, I thought it was completely stupid, right? So we said that we need to do gradient descent. So we need to compute partial derivatives. So we need something which is differentiable. So this nonlinearity is not differentiable at 0, right? It has a kink. So that's already something which seems bad. Secondly, you want to have some signal, right? If you want to update your parameter theta, you would like to have a gradient which is non-zero so that you know in which direction to move. Well, again, this linearity seems garbage because for a big part of it, half of the real line, your gradient is 0. So you get no information in which direction you should move. Okay. So this is at first sight. In practice, you see that it's one of the most successful nonlinearities in neural networks. And I don't know about the theory, it just feels very strange, but it is what it is. And so this is one example of where we don't actually use something which is differentiable, which was an assumption. It is differentiable almost everywhere, except at one point. But yeah, that was something that I found interesting. Okay, so we have all the pieces that we need. So let's see an example of applying machine learning to artificial life. And specifically to Lenya. Okay, so yeah, so supposedly I showed these videos last time, but I didn't have time, so let's see them today. So what we want to do is find some parameters for Lenya that generate creatures which are stable and that move around in some predefined direction. Okay, so this is an example of a paper that I linked in the references, where they took Lenya and they trained it exactly for this purpose. So they trained it to be very stable and to be able to navigate these environments where the blue things, or here the black things, are essentially walls. Okay, so they're walls in what sense? Anything that comes in contact with them is set to 0, essentially. Okay, and so here you see these evolved, creatures which are very stable, which is very uncommon for Lenya. Okay, if you choose parameters even quite cleverly, it's very rare to have creatures which are so resilient. And so here you can see that they didn't learn to navigate a maze. They learned to kind of hug the walls until you get to the end, which is a good strategy. But okay, so these creatures, they were evolved using machine learning. So how was it done? So in a few words. So in this specific example, the parameters theta are the real numbers that tells us the shape of the kernel and the growth function. Remember, that's all the parameters that we have for Lenya. What is the input? Well, the input is simply the world's initial condition, okay, which is a tensor of this shape. So in this specific case, since we want to spawn a creature, it will probably be good to choose an input which has a localized excitation. Okay, so for example, for the initial state of the world, we will take something like this, which has a localized excitation, such that our creature can indeed emerge. Okay, it's unreasonable to take just a random initial condition because it will be very hard to spawn a creature from that, consistently at least. And okay, our f theta of t is simply the Lenya evolution rule, which we apply this amount of times, such that we evolve for time t. And finally, and more importantly, what is the loss? So in this case, what we want to do is make a creature that moves to the right, okay, for example, or in this example, to the left, to the left, okay? So our loss should reflect what we want. Okay? In this case, what we can do is choose an ideal end state. So this is a world state where the creature is moved to the left. And the loss, okay, we have to translate our want into a single number. So the loss could be the squared difference between the final state that we obtained and the desired final state. And we take the sum over all the square difference in all the pixels. Okay, so this is a representation of what we mean. So the orange square here is the initial condition. So we initialize with everything dead except a square of excitation. And the red shape here is the location where we want the creature to be at the end, right? So what we do, and the green shape here is the location that the creature happened to be after the evolution steps. So we take the difference between these two images and sum the square of the difference. This gives us a single number, which tells us how well the creature reached the target. And then we have our loss, our parameters. We can just apply the gradient descent algorithm. And in principle, we'll find some parameters which make the creature move more and more towards this target. Okay. In practice, you may have some problems. Okay, these are vanishing gradient problems, because if we start here and want the creature to end up here, right? Imagine that the creature goes to the left but ends up here. So you see that here, if you change the parameter a little bit, your creature might move a little bit up, but it still will completely miss the target. Okay, so in other words, if the creature ends up here, or if the creature ends up here, the loss is exactly the same. So there is zero signal. Okay, if I take the partial derivatives of the parameter with respect to a creature arriving here, it will just tell me, you can choose the parameter as you wish, you will have no change in the loss. And this is a big problem, right? We have zero signal to know how to move the parameters. Okay, so in practice, that's a problem of choosing the correct loss, okay, which is a big part of it. So in this case, what they did is that instead of starting with a target which is extremely far from the initialization condition, they first choose a target which is slightly to the left, so that you make sure that your creature always intersects the target in some way. So that way the creature always gets signal in how it should change its parameters, okay? And then you move the target little bit by bit as the creature learns to go left. And so that's how it learns, okay? This is called curriculum learning. And that's how they solve this in this specific case. And okay, it managed to work reasonably well, as we've seen in this video, although sometimes it is quite unstable. So for example, let's see here. Yeah. So sometimes you have instability which are due to linear. Okay, so for example, okay, now this is not the example. It's after that, yeah. So here you have failure cases where the creature just dies, or sometimes it just explodes, right? And so this is very annoying with Lenya because, of course, again, if your creature just dies, you would just get a loss which is very bad and which gives no signal, right? Because if you die away from the target, I mean, you can change the parameters a little bit. Maybe you will die here. Your loss is exactly the same, so there is no derivative. And so, yeah, all that to say that it works for Lenya, although it's very finicky. You have to be very careful with the loss. In flow Lenya, it works much better because you don't have to worry about this explosion and this death. Okay, so this is an example where they trained a flow Lenya creature to move to the right. And okay, it works as well as with Lenya. And here it's funny, you can see it left behind a bunch of matter. Okay, but okay. So this is one example of using machine learning to design some emergence of complexity. Okay, so here we wanted creatures to emerge from our rules, and we want them to move somehow. We designed a loss function for this. We're able to do it. So neural cellular automata, it's essentially all about that. Okay, it's using gradient descent to reach a specific goal. So okay, so we want to design a cellular automaton which is which is crafted with the fact that we want to apply this gradient descent on it. Okay, so Lenya was not designed with that in mind. It still works reasonably well, but very finicky. So here we want a cellular automaton which is made to be used with these machine learning algorithms. So what are the requirements if you want to use this machine learning, this gradient descent on it? So one requirement which is important, is to not clip the output values. Okay, so remember in Lenia, we clip the values of our world between 0 and 1 because we don't wanted things to explode. But the problem with the clipping is that it also sets all the gradients to 0, right? If you're at the point where the values get clipped, you get no information on how you should move through gradient descent. Okay, so we will not clip the values of our model. And additionally, to compute the transition function, we will use a simple neural network, okay, which will be composed of a few layers. And the next state of the automaton will be computed by sending the world through this neural network. So that way, if we have a neural network which implements our evolution rule, we can use the usual machine learning libraries like PyTorch, for example, to do our gradient descent. Okay, we don't have to implement it ourselves. So the model that we're going to talk about today, and it took quite a bit of time to arrive here, but here we are, is a neural cellular automaton, and it does precisely that, right? It's made with the learning, it's designed keeping in mind that the goal is to learn morphogenesis. Okay, the learning objective is really morphogenesis. So this is what we saw also during the reaction diffusion course. So the morphogenesis we want to do here in particular is start with a single pixel. Here we have a single pixel which represents an egg, and we want to evolve it through some cellular automaton dynamics to get some picture. Okay, for example, this lizard here. So let's set a few rules that we want to respect to make things non-trivial. We want this morphogenesis to be emergent, this organization to be emergent from some local update rules. So we will enforce the fact that each pixel can have information only about its surrounding pixels, okay, what we usually do with CAs. And additionally, each pixel in our world should use the same update rule. Okay, you're not allowed to say, okay, this pixel here will use this update rule such that it becomes an eye of the lizard. Then this pixel here should be the tail, so it will use this other update rule. No, each pixel in the image is applying the same exact transition function as its neighbors. Okay, that's quite restrictive. But that's more or less what cells do in our body, right? So, okay, the cells, they differentiate, but at the beginning, your cells just apply the rule of physics. I mean, they all have the same rule. Yeah, and finally, our model should be differentiable. So our transition function, we should be able to differentiate it to allow for machine learning training. Okay, so just to say, because I didn't say it, so this neural cellular automaton was invented by the team at Google, so Alex Morvintsev, Ettore Randazzo, and Eivind Niklasson. And there is also a fourth author, which I forget, but you can find it in the references. So, okay, let's begin by defining this cellular automaton. So it's quite familiar to us. It's just a cellular automaton, so it will be very simple. So the world, which will denote like this, Ci x of y. Again, it's a two-dimensional cellular automaton. So it's fully described by a tensor of shape CHW. So in other words, at each pixel, you give me C values, C real values, which denotes the state of the pixel. Right, so the different values that a pixel carry, we call them the channels. Okay, so you will have the red, green, and blue channels, which will determine how the pixel appears. But there will be also a bunch of other channels which are not visible to us, but which the model can use to evolve. Okay. So it's what I say here. So the first 4 channels of the pixel will be its red, green, and blue value. And the fourth one is the alpha, so how transparent is a pixel. The rest of the channels, they are hidden. Yes? Right, so this you can choose in principle. In practice, we will use 12 hidden channels and 4 visible channels.
Yeah. So, I mean, is it required to have that many for it to work at all, or if I only have...
That's a good question. I didn't try. I think you can make it to reasonably work with less channels than that. It will depend the complexity of the things you want to do, I think. But that's a good question. Yeah, I haven't tried too much. I assume that the parameters that they chose in the paper are kind of the minimal ones that give good results. But yeah.
Because
Yeah.
last time we saw a demo of this.
Yeah.
You could like erase nodes of pixels and
Right.
regrow them parts.
Right.
But that is trivial to do if you just copy the information from all the visible channels into invisible channels.
Right. No, but so when we erase, we actually erase all the channels, even the invisible ones. So you really erase all informations. Yes. So yes, so we have, this is our state of the world. Each pixel has a bunch of values which determine its state and how it appears. And the dynamics now, we will define the dynamics. They will be separated into two steps. Okay, so first, each pixel will look at its surroundings, perceive its surroundings, and summarize the state of its surroundings in a vector. And then using this summary, it will apply some sort of complicated function to determine its new state. Okay, so in that way, it's very similar to what was happening in the LGCA, if you remember. So in the LGCA, first you had the movement step where you move each of the gas particle, and then you had the interaction step where you do the collisions, and the interaction step does not depend on the neighbors, right? So here it will be exactly similar to that. So let's talk about the first step, the perception step. So in this model, you can change it, but we'll use the simplest neighborhood of a 3x3 square. So each pixel has access to only the more neighborhood around him. So in the original paper, what they do is that the way that the particle perceive the neighbors is not a parameter of the model. Okay, it's completely fixed. You cannot change how the particles perceive the surroundings. Okay, so that's what we will explain. So what are the particles doing? They are just perceiving their neighbors using these two kernels. Okay, these kernels are called Sobel filters. So here it's as usual. What does it mean? It means that the pixel, we compute the sum of the neighboring pixels weighted by these values. So what happens if I apply this filter to an image? Okay, so here I'm doing something very meta. So I'm applying this Sobel filter to the definition of the Sobel filter. So how do we apply it? We just go over all the pixels in the image, compute the new value according to this kind of kernel, and then that's the value of the new pixel. So you see that this, so this is the result of applying S of X to this image, okay? And this is the result of applying S of Y to this image. So we see that S of X picked up on all the vertical lines, right? So we have extracted the vertical lines in this image, whereas S of Y extracted all the horizontal lines, okay? So that's what the Sobel filters are doing. They're essentially computing the partial derivative in X of the image for Sx, and the partial derivatives in Y of the image for Sy. So in this image, you have a big change you have a big X derivative when the color changes a lot traveling from left to right. That's why we pick up on the vertical lines, and the same thing stands for the Sy, okay? So if we combine the two, as we can see, if we combine the Sx and Sy filter one on top of the other, we pick up on all the changes in color on the image, right? Because we are essentially computing the gradient. So here is an example. I don't know if it's very visible on there, but so if we take a regular image and then apply the two Sobel filters and sum them, we get something which essentially finds all the shapes that are in the image. Okay, so it's a way to extract the shape of an image. And if you want to go a bit further in terms of mathematics, so if you consider the Sobel filter a discrete version where the distance between the pixel is smaller and smaller, you can show that doing a convolution with Sx gives us the partial derivative in x, okay, up to O of delta x squared. Same thing for Sy. So really these Sobel filters, they are computing the gradient in X and the gradient in Y. Okay. So what it means is that when a pixel perceives its surroundings, all it can see is how much things are changing in the X direction and how much things are changing in the Y direction. It cannot access the value of the surrounding pixels directly, right? Right, so the rule for the perception step is combining this perception from the two Sobel filters. So we first compute the transform with the Sobel filter X, then the transform with the Sobel filter Y, and we do this for each channel separately. Okay, so it will essentially compute the partial derivatives for all the channels of the image. So if you have 12 channels, you will get 12 partial derivatives for Sx, 12 partial derivatives for Sy, and we add to this information the information of the current state of the cell itself. Okay, so if we combine these three elements, we get a new description of the world after perception, which is of shape 3CHW, right? So now each pixel knows not only its own color, but also the partial derivatives for all the channels. So far, so good. So this is a pictorial representation of what's happening. So we have a picture here. So if we zoom in on a pixel, this is a pixel and its neighbors, okay? And here we represent all the different channels that we have. And to each of these channels, we convolve it with Sx and Sy. And we get a new vector. Okay, this is the new vector that represents this single pixel. And it tells all the values of the pixel and then all the derivatives for each of the channel and all the X derivatives for each of the channels. Okay, so we have this new vector which contains more information. And this is the perception step. Okay, so just a small note. Instead of using a Sobel filter, we could choose here to have just any arbitrary kernel. Okay, we could set the values of this kernel to be parameters of the model that it has to learn as well. So in that case, the model would have to learn to also perceive in an efficient manner. But here we leave the Sobel filters as is. Okay, and the original paper, the reason for this is that the idea was that, okay, you have the RGB channels, which is the actual color of the cells. And then the rest of the channel could represent some concentration of some chemical. And the idea was that, apparently, I don't know if it's true or not, in biology, you can usually sense the chemical gradient, but not the concentration of the chemical directly. Okay, and so this, using the Sobel filters, was a way to emulate the fact that the cells should be sensitive only to the chemical gradients, but not to the chemical concentration directly. Okay, it makes things a bit simpler in our model, and so we'll keep that. So we're gonna do the break, so come back at 15:20. In the meantime, you can think about the second question, which is whether the perception step that we described preserves approximate rotational invariance or not. And we come back in 15 minutes. So let's restart a bit early. So where were we? Yeah, so this question here, so there hasn't been that many answers, but I assume it's because people are a bit confused. So the question is the perception step rotationally invariant? And I would say that the correct answer is it breaks it for me, but maybe it was a bit misleading, the question. So the perception step, it breaks rotational invariance. You can see it because, I forgot to add the image. You can see it because you can compute the value of your perception vector. If you give an input a line like this, it will be different from the value you get if you put as input a line like this. Okay, simply because this line will trigger the Sobel Y, but not the, I mean, sorry, it will trigger the subble X, but not the subble Y, whereas this line will trigger the subble Y, but not the subble X.
But we just add that happening, right? Like we don't treat those two channels separately.
No, you do. So sorry, yeah. So if that was not clear, that's good that I asked the question. So you do not add them, but you concatenate them, the outputs. But otherwise, you're right, yes. So if you added, I think you need to add the square of them, maybe, to get. Yeah, exactly. Yeah.
Because that's the edge effect algorithm I've seen before.
Right, and this one is rotationally invariant, yes. But here we really concatenate them. So you keep the information which is directional, and if the information is directional, you cannot be rotationally invariant.
So the images we showed above, for example, right? If you scroll back up to the
Yes.
This you must have squared it, right? Because you cannot get
This one here. Yeah, so this one is the sum of the two square. Yes, exactly. Yeah, exactly. So this is the sum square. Yeah. And this is the individual ones where we keep, and these are, yeah. Yeah, thank you. If that was not clear, that's good that I asked this question. Yeah, so they break it because we keep the information, but of course you could have kept it rotationally invariant if you took a proper combination of the two, and this is what you suggested. So if we square these results and add them, we get something which is rotationally invariant. But even though we are not rotationally invariant, we are rotationally equivariant. Okay, that's a word that you know if you study a bit of group theory. So what do we mean by that? We mean that our observations will change according to our rotation of the world in a way which is compatible with the rotation group. Okay, so let me show you what I mean. So if we rotate our world C, okay, we say that we apply the rotation to C. So this is a 90-degree rotation as an example, but it works for any rotation. We can see it as the same thing as taking C and rotating the coordinate system in the opposite direction. Okay, this is the difference between an active rotation and a passive rotation. So then our perception vector is this thing, and you can compute that this thing is equal to applying Sy on the first channel and Sx minus Sx on the second channel. That's what the rotation do. And then you can notice that Sy is equal to Sr minus 1 of x. Okay, so if you rotate x by minus 90 degrees, you get y. And minus Sx is the same as the Sobel filter according to R minus 1 of y, which is minus x. Okay. So as you can see, applying S to the rotated world is the same thing as applying the rotated S to the unrotated world. So in that sense is what we mean by our rules are somewhat equivariant. They do change the state of the system if we rotate our world, but they change it also by a rotation, essentially. Okay? And this will be important because if we train our model with the Sobel Sx and Sy, we get some parameters. And then we say, okay, let's take the model with the same parameters, but just rotate the Sobels. It should rotate our image precisely because of this equivariance. Okay? Rotating the Sobel filters is equivalent to rotating the image in the opposite direction. So this is a fun fact about this model. Yeah, okay. And I just saw that there was a comment about Hassan, which worked a lot with these NCAs, that said it is kind of rotationally equivariant, which is exactly right. And he also told me that apparently what I call the computation step, it's called formally by the Google team as adaptation step. Okay, just a nomenclature again. So what is the computation or adaptation step? So after the perception step, we have this new vector of information about our neighbors, and we want to process this vector into our new state for the cell. Each cell will process this vector, okay? Just like in LGCA, as I said. And this is also where all of our free parameters will be. And how will we process this vector of information? Well, very simply by a two-layer neural network, okay? With a nonlinearity in the middle for the usual reasons that I explained. So pictorially, this is what happens. So each cell is given a perception vector of size 3c, and from this it wants to think about it and compute the new state that it should have. Okay, so to do this, you feed this into the first layer. Okay, you do your matrix multiplications, you apply your nonlinearity, which is ReLU, as we mentioned. Then you feed it in the second layer, and the second layer would reduce the dimensionality to be correct to represent a new state. Okay, and so here we have a choice of how many neurons we put in that layer, or how many hidden dimensions we want in our hidden layer. So the dimensions work this way. So each cell has that 3c dimensional vector, which is the one coming from the observation. And we want to reduce it back to a c-dimensional vector. To a c-dimensional vector such that it can represent the new state of the cell. Right? So the first layer goes from 3c to h, the hidden layer, and then the second one goes back from h to c. And so we can summarize this picture here in this very simple equation. So the output of the computation is just a matrix applied to the perception vector plus a bias. Then you apply ReLU on this, and then you apply another matrix plus another bias. There is just a little bug in the parentheses here. Yeah. And it's like so, yeah. Okay, so just matrix plus bias, nonlinearity, matrix plus bias. And these matrices are a C times H matrix, and the other one is a H times 3C. Okay. How many parameters? We're going to skip this question. It's not very interesting. But to count how many parameters you have, you just count how many real numbers you have in this matrix, how many real numbers you have in this matrix, and then don't forget this vector and this vector. Okay. So the total number of parameters is 4HC plus C plus H. All right. So we have our computation step, which gives us some value, okay, which could be either the new state of the cell after it had observed its neighbors, but we would like to make things a bit more smooth. So instead of being the new state of the cell, it will be how much the cell should update each of its channels. Okay. So yeah, so in this step, the update step, we'll use the C comp to update our state. And so since we want things to grow and stabilize and be smooth, it will be easier to get the new state as a function of the old state plus a small update. Right, so in this way, instead of the model needing to compute exactly which color it should be next, it just has to compute how much to change its color, which is usually more stable. So here we have another thing to introduce, is that we would like to have a notion of alive and dead cells, right? So we would like some cells to be alive such that they do update their state, and some cells to be dead to remain black. And the reason for this is that we want to go from an egg to a lizard, but we would not like for these cells here, which is in the vacuum, to suddenly become alive, right? And spawn the lizard. We would like kind of the lizard to grow from this initial cell. And so we want to put the notion that the middle cell is alive and the others are dead. And then we must specify how does a cell becomes alive, right? So we do this with the alpha channel, so the transparency channel, and we'll say that a cell is alive if any of its neighbors has an alpha which is bigger than 0.1. Okay, so essentially a cell is alive if any of its neighbors is also alive, let's say it. So what will happen to dead cells is that dead cell, we just force them to have all channels be set to 0, okay? And they are not allowed to evolve. So what you get is something like this. So the orange cells here are mature, so they have an alpha which is bigger than 0.1. So these are mature cells. And the cells here, which are light orange, they are growing cells. So their alpha is still below 0.1, but they do have a neighbor which is mature. So they are also considered alive, and they're allowed to update their state. And finally, here you have some cells which are dead, okay, because they do have neighbors which are alive, but they are not mature, okay, so this does not propagate. Right, so what we do is that if a cell is alive, we keep the C computed as it is. If a cell is dead, we just set it to 0 and it just remains 0. Okay, and before going to how to update each pixel, we would like to introduce some stochasticity into the mix. Okay? Instead of updating each cell synchronously, as we usually do in the cellular automata, we'll make it so each cell has 50% chance to update each time step. Okay, so that not all the cells will update at the same time, and that will give it some more of a it will be more similar to living things where not everything happens at the same time everywhere, right? So yeah, so this is very simple. We just say that with 50% chance, a cell just remains its own color. It does not change anything, and that's it. And with 50%, it does all of this perception, computation, etc., and actually updates. Right? So another bonus of this stochastic evolution is that the things that we learn should automatically be more robust, because if it has learned to develop a behavior, it has learned it despite the fact that each cell fires at random. And so it has to have some sort of error correction baked in to take into account what happens if the cell does not update, right? So in the end, the final updated state is computed in this way, okay? So first we get a tensor, we look at which cells are alive before anything happens, okay? So this is A before, currently alive cells. Then we do our process, we do the perception, then we do the compute step, okay? And this gives us the computed state for each of the particles. Then here we draw at random which particle will update and which particle will not, okay? This is an update mask that tells us if a particle updates this step or not. And the new state of each particle will simply be the old state plus the computed state multiplied by the update mask, such that only half of the particles actually update. And in the end, we compute which particles are alive after the update, okay? Because some particles might be dead before but become alive after. And the final updated state is this state here we computed, where we allow the particle to evolve only if it was both alive before and after. Okay, why? Because a particle that was dead before is not supposed to evolve because it's a dead particle. And a particle that ended up dead should also be set to 0. So this is the final state. Okay, it's very simple. So the computed vector that we compute with this thing, we just added to the current state of the system. So here you might notice that we don't have a parameter delta t. So here in principle we could add a small delta t so that our update is more gradual. Okay, that's also works fine. And yeah, so we can take the continuous t limit in principle if we put a small delta t here, and then there is no clipping, everything can work, and I can compute the continuous limit of this. In principle, there is no obstruction to that. Well, there is a small problem, but let's not go about it. And what about continuous x? So continuous x is harder, right? Because the kernel that we choose is fixed and it's of-sized 3 times 3. So it would be hard to see and make the same thing that we did for the game of life, where we blow up the kernel and then take more pixels per kernel, and so it looks more and more continuous. But there is also the fact that the application of the Sobel filter, as you see here, is proportional in principle to 1 over delta x. So if you take a delta x which is twice as small, is kind of equivalent of taking a Sobel filter which is twice as big. So maybe if you change the scale of the Sobel filters, it has the effect of taking the space to 0. And okay, that's a very interesting direction to study, and it will be, I believe, the project from Esan, which worked on this also for his research. So if you want to know more about these continuous limits, stay tuned for his project. Okay, finally, training. So we have our model, we know how it evolves, and now we want to train it such that we go from an egg to a picture, right? So what happens first before training? What happens if I just take our cellular automaton and I just take random parameters, right, for the neural networks? We can, of course, do this. And it gives something that looks like this. So here what I'm doing is I'm putting eggs with my mouse, okay? You don't see it. And changing parameters for each egg. So as you can see, it does some sort of firework, colorful fireworks, which is very nice to look at. But it's very short-lived, right? It disappeared right away. And this is because since we have no clipping on our values, what happens if you choose random parameters, it's that very quickly the updates goes to infinity and everything becomes not a number, and that's when everything is black. Okay. So this model, as opposed to, for example, Lenya, if you take random parameters, you won't get anything of worth because you need to tune the parameters exactly such that it does not blow up, right? But it's still cool that it does some sort of fireworks. But, yeah. And here you can immediately see that it's not rotationally invariant because most of the fireworks are kind of spheres, but some have some sort of direction. And this is precisely because the rules are not rotationally invariant. Okay, so we said we want to do morphogenesis. So the task is very simple. We start with an image, which is an image with both the red, green, and blue, and also the alpha, so the transparency. And we would like to grow into this image starting from this initial condition, right? Everything dead except for a pixel in the middle. And this pixel in the middle has value 1 in all of its channels, right? Not only red, green, and blue, but also all the hidden channels. And we want to go from this to, let's say, this picture of a betta fish. So it's a fish, aquarium fish, which I really like. So we'll try to grow from this to this. So all we have left to do is to impose the loss, right? And we want to impose that the final image is this, right? But of course, the state of our system is CHW with C bigger than 4, right? We may have 16 channels in total. And the fact that we want this final image does not give us any information about what the other channels should be. Okay? And what we do to do the loss is we say, okay, let's not care about the hidden channels. We just ask for the cellular automaton to have the RGBA channels which match this image at the end, and it's free to do what it wants with the hidden channels. Okay. So since the images are continuous data, the common loss which is used in this case is the L2 loss, or the mean squared error. So we take the evolution of our model up to TF. Okay. We look only at the 4 channels RGBA, and we compute, okay, here it was whale, it should be fish. And we compute how different is this final image with the picture that we want. And this is our loss. And now we have all the pieces that we need. Right. So, yeah, just a comment about this TF. So the time we let the automaton evolve. This is a hyperparameter, okay? This is not learned. Potentially it could be, but it could be quite complicated. And it's very important as a hyperparameter because the way we defined our task, okay, all points are dead except 1. It means, and also the points which are dead and surrounded by dead points, they cannot do anything. Okay. So what it means is that we need to grow from our single pixel to our final image, and this speed of growth is limited. Okay. There is some sort of maximum speed that something can move in our system, which I call the speed of light. And this is simply because, okay, if we start with a live pixel in the middle, it will take at least one time step for these surrounding pixels to actually become alive, right? And in the first time step, all the other pixels are not allowed to do anything since they are dead. Then you need at least 2 time steps to reach here, 3 to reach here, and so on and so forth, right? So if you evolve your state for 5 time steps and you ask him to make an image which is 20 by 20 pixels, it's plainly impossible, right? The maximum size of the image it could do is 5 by 5. 10 by 10, right? 5 in both directions. So, yeah, so what we'll do is that, so that's what I said. Yeah, so in addition of growing to the correct size, the model needs to do a lot more, right? So it has to grow from 0 to the size, but it also needs to know, each pixel needs to know where it's located on the fish. It has to adjust the color according to the neighbor. And so in practice, it will need much more than the speed of light, time. I mean, much more light seconds than it would need to create the shape. So in practice, what we do is we take the final time to be roughly twice the minimal amount of time it would need to fill the image. Okay, this is just a rule of thumb. It's not something very rigorous, but that's the time we'll let it evolve. And okay, you might say, couldn't I take a final time which is very generous, like let him evolve for like 1,000 seconds so it can take its time to generate the picture? And in principle, yes, right? Because you just ask him at the end of the 1,000 evolutions, I want you to be this image. And if the model learns to do it in like 100 steps, it's not penalized, right? You're not forcing him to do it in 1,000 steps. So it seems that taking a bigger time, it would simply be strictly better. But in practice, it brings some problems because this is kind of the shape of the neural network we are actually doing the machine learning on, right? So you start at t equals 0 from the input, and for each time you evolve, you send it through this neural network, which is the NCA, right? So if you evolve it for many, many times, you put one NCA, so one layer each time you evolve it. So at the end of the day, when you need to do the backpropagation, you need to do backpropagation through a neural network which has a number of layers proportional to the amount of time you evolve it for. And so if you have a neural network which is very deep, it's much harder to do machine learning and gradient descent because you have a bunch of problems like exploding gradients, vanishing gradients, etc. So in practice, you should not choose a time which is too big, right? It would cause problems. And from the other point of view, also, if you need to have a much deeper network, you will need much more memory to train. You will need much more time, much more computation. Okay, it will be just overall worse. So you should not choose too big of a time. So in practice, in the paper, what they did is they trained it on 40 by 40 pixel images. They trained it for 64 time steps. So this is more than the 20 time steps you would need to fill the 40-40 image. And they use 16 total channels. Okay, so you have 4 channels for the color, and then you have 12 channels, which are these hidden channels, which are unconstrained by the loss. And the last parameter that you need to choose is hyperparameter, is the number of hidden neurons in your computation layer, right? So the number of neurons that you put here. And what they chose is 128, which is relatively low. So in total, the amount of free parameters is about 8,000. So if you compare this to present-day neural networks that are used for other tasks, like, for example, language processing or whatever, it's extremely low, right? It's usually the number of parameters usually in the million or billions. So this is a very small number of parameters, but if you compare it to the alive system, for example, Lenya, where you have like maybe 20 real parameters, it's very high. So it's kind of in the middle of being very sophisticated for an alive system, but very simple for a neural network. So, okay, so let's finally get to the training. So we have all we need. So let's see what are the results. So of course, we want to generate this image, but this image contains about 1 million pixels. So you will need about 1 million training steps to get it with our model. So this is quite a lot, not doable. So what we do is just we rescale it again to about 40 by 40, such that the training can be done, for example, on this computer, it can be done with no problem. And so we impose the loss after 64, and what do we get? We get the following thing, where it works well. So we start from our egg and let it evolve. It generates our image perfectly, and then if we wait some more, it kind of decays, right? Okay, that's already pretty good. So here I put more eggs, and that's what the advantage of the neural cellular automaton, since the rules are completely local, even if you trained it on a small 40 by 40 window, nothing prevents you from actually making it work on a bigger window, right? All the rules are completely local. It does not depend on the size of the picture that you train it on. So it learns very well, but after, if you let it evolve, it decays. So here is an example of the same thing, but different training run. So here it generates a thing, and then it does not decay, but okay, it becomes some mass of the correct color, but not the correct shape. So it looks a bit like cancer, I would say, yeah. And so, yeah, so why does this happen? So we learn to do the shape perfectly, but then always it decays afterwards. And this is a classical case of a misalignment problem, like what we asked it to do with the loss was actually not aligned with what we expected it to do with this loss. Okay. So the main problem is that we ask him to have the correct picture at exactly 64 time steps. We never told him that you should keep this picture after the 64. So it turns out that what it learns is to have something that grows up to 64. If you take a snapshot, it's perfect, but then it either continues to grow or it decays back. Okay, so we want to fix this problem. So what do we do? What you can do is compute for a very big T final, right? If you take a snapshot after 1,000 seconds, maybe it generates the image after 100 seconds and stabilize it for 1,000 seconds. This might work, but it has the problem of the big TF. And what can happen also is that the problem will just slowly grows until 1,000 time steps and then still decay afterwards, right? We still are not telling it to stabilize. So what we can do instead is, instead of taking a snapshot exactly at 64 seconds, each time we train the model, we just randomly sample from a range of final times, and we use the snapshot at some random time in this range, right? So what happens is that the loss makes that the model needs to have the image ready at 64 seconds, but it also needs to maintain the image at least up to 96 seconds, okay? And the hope is that if the model maintains the image for 30 seconds, well, then naturally, if it has the image after 30 seconds, it will also maintain it for 30 more seconds, and so on and so forth. So this is just to show you the training dynamics. So here I have 20 images taken at different times in the training. And so this is what the model learns. Okay. So this is during the training. So you see that at the beginning, it just makes a blob which is of the right color. And then as you go forward in training, it refines the parameters such that the blob looks more and more like the final image. Okay. And so here it's pretty much perfect. And then here I show what happens if you continue for a longer time than what was required. So we see that as time grows on, it learns to somehow stabilize the parameters. Okay, so we see that the thing does not explode as much, but still it's not that great, right? It does not stabilize the image perfectly, although it does better and better. So this is the result after the full training regimes where you trained it up to the maximum. And again, it is more stable than before, right, with this regime. So we see that the fish kind of maintains its shape, but it's still fairly unstable. Sometimes it spawns some kind of children, and over time it becomes worse. So here I am erasing it with my mouse just to show that it has developed naturally some regenerating capabilities, which is quite impressive. And here I'm just putting more eggs. So yeah, so this new training regiment is better, but still not amazing. So what we would like to do is really force it to maintain the image for longer and longer times, but we are limited by the size of the times that we can do, right? Yeah, by the way, this is from the original paper. So as you can see here on this timeline, the green part is where the loss is applied. All the pictures look perfect. But then if you evolve further, you see that slowly, yeah, they get corrupted. And if you go further and further, it's not able to maintain its shape, right? Well, let's go one step further to stabilize it. So the next step in the training regime is sample pool training. So what we do is that we prepare a pool with n samples, which we initialize to be all the egg state. And this pool here will determine the initial condition of the model. So during training, what we do is first you sample from the pool, and this gives you the initial conditions. You evolve these initial conditions for, let's say, 60 seconds. This gives you a final state, and then you apply the loss to this final state. But then what you do is that you take this new final state and you put it back into the pool. And what happens in this way is that the model needs to learn to go from the egg to the fish, but it also needs, because you take sometimes his final state and put it as initial state, it also needs to go from the fish to the fish, right? So it needs to learn to also stabilize the fish. So in this way, essentially, we are effectively simulating the model for like 1,000 time steps, but in snippets of 60 seconds, right? First go from egg to fish, apply the loss, then grow from fish to fish, apply the loss, and so on and so forth. And so this solves the problem of having it to simulate for like 1,000 time steps at the same time, right? So the model needs to learn to go from 0 to TF, but also from TF to 2TF, 2TF to 3TF, and so on and so forth. So this seems great, but it has some potential problems. So at the beginning, the model is generating garbage, right? As we've seen, it's generating just a blob of color. But then, because of the pool sample training, we are taking this garbage and asking the model to make the fish starting with this garbage. This might be super difficult. So if he cannot recover from garbage to fish, it will just make more garbage. Then we take this more garbage, we put it in the pool and ask him again to generate the fish from the garbage, and then this is unstable, right? So to stabilize this, what we do is that when we look at the output of the model, we'll just discard the outputs which have the bigger loss. Okay, so the worst outputs we do not add back to the pool. We just add the outputs which are reasonably good, such that the model does not need to start from garbage, it starts from things which are reasonable, right? And the other thing is that as the training continues and the pool does not contain any eggs anymore, we are now training the model to just go from fish to fish. So it might learn very well to stabilize the fish, but it might forget how to go from egg to fish, right? So just to prevent that, this is very simple. We always include at least one egg in the sampling of the pool, right? We force one of the initial conditions to be the egg, such that it has to remember how to go from egg to fish. So if we train it like this, the result is this. And as you can see, now the fish is very stable. Here I put some more eggs. So the model has learned to perfectly stabilize the fish. And yeah, so here I just show what happens now. Now we want to see if the model also has learned to repair the fish. Because in some sense, during the pool training, it has to go from mild garbage to again to a fish, right? So maybe it learned to repair the fish on its own. So let's see. Kind of, right? So if I damage the fish a little bit, it manages to regenerate it. But if I damage it too much, it stops being able to recover, right? Okay, so here we see that these fish have been severely deformed, but it's still stable. That's interesting that it's still stable. Okay, so let's see here a bit more rigorously. So here I take the initial fish, and then here I cut the fish in half in all possible directions. And we look at how much it can recover. And it depends on what you cut, right? Here we cut the top, it did not recover at all. Here we cut the head, it recovered pretty good. This one we cut the tail, not so good. So it has some repairing capabilities, which is very impressive on its own, because we didn't ask it to do that. But they're not as good as they could be, right? So let's try and see if we can train it to self-repair even better than that. Okay, so this is an example from the original paper again, where they damage, and you see that sometimes it managed to repair, but sometimes not at all. So how do we incorporate this into the training? Well, this is very simple again. All we have to do is to damage the initial condition such that it needs to learn how to repair it to get a good score. And to do this, it's very simple. We take a sample from the pool, but before giving it to the model, we just drill a hole through it and give it this new state as initial condition. And we tell him, okay, you have to get a fish from this initial condition. And that's what we get. So as you can see here, we start from the severely damaged fish, and it manages to regrow them quick and perfectly. Okay, see here, I just want to show you, because you can also play with it if you want. So here I have several checkpoints of the trainings that I did. So here, if I take the repairing beta, sorry, yeah. So by the way, if you take an image which is not too big, training this model here takes about 20 minutes on this laptop with a GPU. So it's very efficient. So here we have the model. Okay, it learned. And now I can go and erase. And as you can see, he manages to repair it flawlessly, right? I can really damage it. It regrows anytime. Okay, if I damage it really extensively, this is something it hasn't seen in training. But despite that, he manages to grow back, right? Yeah, so I don't know how much you can push it. I don't think you will be recovering from this. Maybe, yeah, okay. So it's really impressive, the repairing capabilities that it can learn. And here you can also put more eggs. And one cool thing to try is to put 2 eggs close to one another, because then we'll try to grow and they will kind of come into conflict. So it's interesting to see how they resolve the conflict. So here they resolve it perfectly. If you leave a bit more space, yeah. So sometimes they just are happy to sit like that in a combined fish. And yeah, it's very interesting. Yeah, so here you see like the head touch the tail of the other fish, and there is something going on here, I don't know. But it's very interesting, the kind of emerging capabilities that come from this kind of training. So there are a lot of things to try with this. I recommend to try and train your own picture. It's very fun to see what happens at the end. Yeah, and another thing that I wanted to show you is that so we see only the RGB values, right? But there is also these hidden channels, which we have no idea what they're doing. But in principle, what the hidden channel do is that they store some information about what each cell is, right? Because these cells can access only its neighborhoods, but because it grew up from a single egg, it may have kind of understood where it's located on the fish during the growth process. So indeed, if we go here, you can, wait, it's not active. Let me see 1 second. I think I didn't push the code to see also the hidden channels. Yeah, no, the code is not there. Okay, so let's do it the video. So here in this video here, on the left, you have all 16 channels that you can that are visualized. Okay, so blue is negative and yellow is positive. So here, this is just the RGB channels. This is the alpha channel. You see that this designates essentially the live cells, which is trace the contour of the fish. Then you have all the other channels, which are, yeah, they're very peculiar. I mean, I couldn't tell you why they developed this, but it's quite interesting. So you see here, you have a separation of two halves of the fish. One half is negative, the other is positive. Here you have a more complex separation. Here, this one is very interesting. So the interior of the fish is all negative, and the outline is yellow, so positive. So the cells have learned if they are on the outline of the fish, right? Here, it's also an outline kind of thing. And okay, it's very hard to tell what they learned, but what they did learn is actually useful for the evolution of the fish. So this is kind of interesting as well. And so related to that, I don't remember if it was just somebody that told me about this, or it was on a paper, but people tried to see if each pixel knew its own position, despite being able only to look at its surroundings. And to do that, what they did is that they trained a very simple linear layer to take the channels of a pixel and to output the position of the pixel, okay? And so, in principle, if somehow the pixel has stored the information of its position, you should be able to extract it just with a linear transformation. And people observed that this was indeed possible. Okay, so it was possible to kind of train a probe that, given a pixel in the fish, would tell you, I am the pixel at position 22, 24. Okay, so somehow during the growth process, there is a signal propagation that the pixels exploit to learn about their position, and that's how they are able to maintain this color perfectly. Okay, at least that's one way. And so I had a question about this, but we have little time, so I'll just speed run through it. So the question was this. So we have this target here, which is completely uniform in these two colors. And the question is, can we train NCA to make this image and also be self-repairing? Okay. So the reason I ask this question is because intuitively here I would have thought, okay, no way it can do that initially, because the pixels know only about their neighbors. So what the pixel sees here and what the pixel sees here is exactly the same thing, right? Because the color is uniform. But of course, this is forgetting about the hidden channels, right? The hidden channels here and here can be different and probably will be different, such that the pixel can actually tell where they are in the square. So I was expecting that the answer is definitely yes, you can train a self-repairing NCA from this. But in practice, it turns out to be much harder than something which is not as uniform. So I can show you here, I actually tried to train this. So here is the result. Right, so it manages to grow into the square, no problem, and to uniformize. But once it's uniform, it can recover from small kind of perturbations. So it has learned to do that at least. And we see that when we perturb, there is kind of a wave going outwards. I assume that maybe this wave is kind of computing where it's located on the square. But if I do a bigger cut, this was no problem for the fish, right? This has trained exactly in the same way for the fish, and we see that it struggles to recover. Okay, so in some way, it seems that I think it must be able to do it if you train it properly, but the fact that the colors are uniforms actually make it harder. So it means that it is still relying quite a lot on the actual colors of the pixel instead of just relying on the hidden channels to do the thing, right? So yeah, so this was quite interesting and surprising to me, but yeah.
How wide, how many pixels is the square inside and outside?
I think it's the ratio of the two squares, you mean? Or
No, the actual pixel size.
the whole square. So it's about like 30 by 30.
And the inside?
And the inside one, I know, yeah. So the big one is like 35 by 35, and the inside one I'm not sure. Yeah, probably 15 by 15, something like that. Why is that? Yes.
Because if you have 12 square channels, then I would expect it to be able to do things that are up to a width of 12 of a uniform color. It can still include the fact that it's, like, it can compute up to the 12th derivative in a sense. Beyond the 12th derivative, I would have.
I see what you mean, but in practice, yeah, I see, because you're allowed only to encode. Yeah, maybe that's a good point. Maybe that would be an experiment which would be worthwhile.
If you do a Fourier analysis and you have four
Yeah,
harmonics and you can encode up to a certain.
yeah, that's true. That's true. But here the channel could yeah. Yeah, I'm not sure. Maybe that's true, but it's not clear to me because you see that in the channels you can actually contain the information of where you're located. So maybe you can kind of find a trick to do more, but maybe it's related to that indeed. So you see here it completely degenerates. So it knows kind of the local thing is to have a orange band in red, but it doesn't manage to keep the global thing. So yeah, so the answer is it manages to learn that, but not quite as well as the fish. And okay, so I think I'm gonna stop here. That was the main thing that I wanted to do. So there were a few things which are extension to this model. So just in 2 minutes. So what if we want to learn for a creature that moves? Is this possible? The answer is yes, kind of. So these are some experiments that I did. Then you might ask yourselves, okay, can you learn to have a self-reproduction, right? So you could ask an objective, which is to go from the egg to a creature plus the egg. There was a paper about that, so you can take a look at this if you're interested. And then finally, there is the question of, can you have several creatures in the same world? Always the same problem. Okay, if we can have our fish, it's fine, but how are we going to have open-ended evolutions? And so here, if you're interested, you can take a read about this part of the notion. So here I modify the rule. I add some sort of DNA channels, which determines which shape you will evolve into. And the most interesting part is that if you cross the DNAs, you actually get crossbreeds which are completely like untrained, right? I never trained to get kind of the half triangle, half square, half red, half blue thing. It just emerged automatically from when I crossed the DNAs. So this is a project that I had, a research project that was 1 year ago that I kind of abandoned. But if this is interesting to you, let me know. I probably will go back to work on it at some point. And then at the end, you can also look, there are some variants. So this is a variant where the actual rules are rotationally invariant. You can still grow stuff. And finally, there is this thing, which is somehow the same thing, but instead of training pixels and rules for the pixels, you train particles and rules of particle interactions, and you can train them to make shapes like this. Okay, that was a bit fast at the end, but I said what I wanted to say about the NCA, so that was the key. And if you're interested in all those differences, I suggest you take a look at the rest of the notion. Okay, so I will be seeing you in 3 weeks. And I will let you know if the next lecture, it's probably not next week, but the week after. And it will be Clément giving this lecture about the KdV equations and solitons. Okay.